Imagine a world where the very air you breathe is saturated with vaporized gemstones, and the rain falling from the sky isn't water, but liquid iron hot enough to melt through a titanium hull in seconds on WASP 76b. A tidally locked gas giant. Temperatures soar to 2400 degrees Celsius, turning metal into mist on the day side before hurricane-force winds whip it to the dark side, where it condenses into a lethal metallic downpour. This isn't science fiction or a fever dream of an astrophysicist. It is the atmospheric reality of the extreme exoplanets we have discovered in just the last decade. Today, we are stripping away the familiar comforts of Earth to explore the most violent weather in the cosmos. From planets where it rains shards of vertical blasts to ice giants that squeeze simple carbon into massive, high-speed diamond hailstorms, you will discover how gravity can turn a gas into a metal, why some planets are literally evaporating into space, and the secret chemistry that allows a cloud to be made of rubies and sapphires. To understand these alien storms, we have to start with the most famous phenomenon in the outer solar system, the diamond rain of Neptune and Uranus. While these planets look like serene blue marbles from a distance, their interiors are pressure cookers of incredible scale. Deep beneath the layers of hydrogen and helium, the pressure becomes so intense that it forces carbon atoms to snap together into crystalline lattices. It begins as a soot-like methane slush, but as it sinks deeper toward the core, the intensifying weight of the atmosphere above performs a feat of alchemy. The carbon crystallizes into diamonds, some potentially as large as boulders, which then rain down through thousands of kilometers of liquid mantle. This isn't just a vertical fall. It is a slow, grinding descent through a superheated fluid that acts like a conveyor belt, dragging these gems toward a core where they might eventually form a layer of solid diamond thousands of miles thick. We value diamonds for their rarity, but on these ice giants, they are as common as gravel in a driveway. The physics behind this was long debated until researchers used high-powered lasers at the SLAC National Accelerator Laboratory to recreate these conditions on a microscopic scale. By blasting plastic film with X-ray pulses, they witnessed the carbon separating from the hydrogen in real time, proving that diamond rain is a fundamental feature of intermediate mass planets. But if diamond rain sounds exotic, it is nothing compared to the silicate storms of HD 1899733b. This planet is a deep cobalt blue, looking almost like a twin of Earth from a distance. However, that blue color doesn't come from vast oceans. It comes from an atmosphere filled with silicate particles, essentially tiny grains of glass, because the planet is so close to its parent star. Its winds reach speeds of 8,700 kilometers per hour. That is 7 times the speed of sound. At those velocities, the glass rain doesn't fall downward. It moves horizontally, a screaming vortex of jagged shards that would sandblast anything in its path to atoms in milliseconds. The blue hue we see is the result of Rayleigh scattering, the same effect that makes our sky blue, but amplified by a literal global sandstorm of molten and solidified glass. This brings us to a crucial realization about exoplanetary weather. Temperature and pressure are the ultimate sculptors of reality. When you push a planet's temperature past a certain threshold, the very chemistry of minerals changes. Take HATP 7b, a gas giant where the clouds are thought to be composed of corundum on Earth. Corundum is the mineral base for rubies and sapphires. Because this planet is tidally locked, one side always faces its sun, creating a permanent furnace. The winds are so powerful they transport this mineral vapor to the slightly cooler night side, where it condenses. Imagine standing on a world where the clouds aren't puffy white water vapor, but shimmering, opaque banks of liquid jewelry, occasionally shedding droplets of molten sapphire. The scale of these weather systems is nearly impossible to visualize. On Jupiter, the Great Red Spot has persisted for centuries, a storm larger than our entire planet. But on ultra-hot Jupiters, the energy input from the host star is so massive that the entire atmosphere is in a state of permanent supersonic upheaval. We see evidence of thermal inversion, where the upper atmosphere is actually hotter than the lower layers because of the absorption of stellar radiation by titanium oxide and vanadium oxide gases. These chemicals act like a heavy sunscreen, trapping heat in the high altitudes and creating a stratified nightmare of temperature gradients. In these environments, the transition from gas to liquid happens in ways that defy our intuition. On Kelt 9b, the hottest exoplanet discovered to date, the day-side temperature reaches 4,300 degrees Celsius. That is hotter than the surface of most stars. At this heat, molecules cannot even hold themselves together. Hydrogen molecules are ripped apart into individual atoms on the day side, only to recombine on the night side, releasing a burst of energy that fuels even more violent storms. It is a cycle of atomic destruction and rebirth that powers winds so fast they defy traditional meteorological models. The transition from these hot gas giants to the even weirder lava worlds reveals another layer of atmospheric horror. Planets like 55 Cancri e are so close to their stars that their surfaces are essentially molten oceans of silicate rock. The atmosphere here is actually vaporized rock. When this rock vapor drifts toward the shadows of the planet's dark side, raining pebbles and stones back into the magma seas, it is a cycle where the ground itself becomes the weather. These worlds represent the extreme end of the planetary spectrum, where the boundary between a solid planet and a ball of gas begins to blur. But perhaps the most mind-bending state of matter occurs in the interiors of giant planets like Jupiter and Saturn, where we find liquid metallic hydrogen. Under the crushing weight of thousands of kilometers of atmosphere, hydrogen molecules are squeezed so tightly that their electrons are squeezed out of their shells. The gas begins to behave like a liquid metal, capable of conducting electricity. This metallic ocean isn't just a static layer. It is a churning, roiling dynamo that generates the massive magnetic fields we see protecting these planets. Scientists believe that within this metallic sea, even stranger things occur, such as helium rain. As helium becomes insoluble in the metallic hydrogen, it forms droplets that sink toward the core, releasing gravitational energy as heat. This explains why Saturn radiates more heat than it receives from the sun. It is literally powered by an internal rain of liquid helium. To find these details, astronomers use a technique called transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere. By analyzing the specific wavelengths of light that are absorbed, we can identify the chemical signatures of iron, sodium, and even glass. It is like looking at a shadow and being able to tell not just the shape of the object, but what it's made of and how fast its heart is beating. This technology is moving us from simply finding planets to characterizing their climates in vibrant detail. We are finding that extreme is the default setting for the universe. Our calm, water-based weather is an outlier. The diversity of chemical weather systems is a direct result of the specific elemental abundance of each star system. A star with more carbon than oxygen would create planets where the clouds are made of thick, tar-like hydrocarbons or even soot, and the rain might be a drizzle of liquid oil. We call these carbon planets, and they represent a completely different branch of planetary evolution where the chemistry of life, as we know it, would be impossible. Yet the weather would be stunningly complex. Consider the implications of wind speeds on these worlds. On Earth, a Category 5 hurricane has winds of 250 kilometers per hour. On the exoplanet HD 189733b, The winds are 30 times faster. At those speeds, the friction between the air and the surface, or the deeper atmospheric layers, creates immense static charges. These planets are likely illuminated by lightning bolts thousands of times more powerful than anything seen on Earth, arching through clouds of molten metal or glass. Each flash would reveal a landscape of roiling, metallic clouds and liquid horizons, a strobe light effect on a planetary scale. These storms also play a massive role in the lifespan of the planet itself. A process called photoevaporation occurs when the intense radiation from a star hits the atmosphere of a close-in planet, heating the gas so much that it reaches escape velocity. Some planets are trailing huge tails of gas, like gargantuan comets, as they literally boil away into the vacuum of space. The iron rain on WASC 76b is just one part of a larger story of a planet being slowly dismantled by its own sun. As we look at these distant infernos, we gain a better understanding of the fundamental laws of physics. They are natural laboratories where matter is pushed to its breaking point. When we observe a planet raining iron or squeezing carbon into diamonds, we aren't just looking at a curiosity. We are seeing how gravity, heat, and chemistry interact when the dial is turned to 11. It forces us to rethink the definition of a planet. Is it a stable rock? Or is it a dynamic, ever-changing engine of chemical transformation? Future telescopes like the Habitable Worlds Observatory, or even more advanced versions of James Webb, will allow us to map the weather on these planets in even higher resolution. We might one day see the glint of a diamond storm or the reflection of a star on an ocean of liquid iron. For now, we rely on the data points and the laws of thermodynamics to paint these pictures. They remind us that the universe is far more creative than our imagination. In the vast darkness of space, there are worlds that would seem like visions of hell to us, governed by storms of metal and jewels, where the very concept of weather is redefined by the extremes of the cosmos. The exploration of these extreme exoplanets is more than a search for a second Earth. It is a journey into the heart of what matter can do when it is unconstrained by the mild conditions of our home. Every time we find a planet with supersonic glass winds or ruby clouds, we are reminded that Earth is a quiet, fragile blue sanctuary in a gallery of cosmic monsters. The next time you see a storm cloud gathering on the horizon, remember that somewhere out there, trillions of miles away, a cloud is gathering that is made of vaporized iron, preparing to release a downpour that would reshape anything it touches. The universe is not just big, it is violent, beautiful, and stranger than we can ever fully grasp. If you found this glimpse into the extreme weather of our galaxy fascinating, consider exploring how we actually detect these distant worlds through the slight wobble of stars or the dip in their light. The more we look, the more we realize that our own planet is just one tiny, calm corner of a much more chaotic and shimmering neighborhood.